Hello, and welcome to the AWS Research Seminar Series. I'm Erica Cox, Program Manager for the Higher Education Research Team at AWS, and I will be your moderator for today. I am pleased to be joined today by Dr. Amir Bahmani, who will discuss deep data needs and challenges in precision medicine. Dr. Bahmani is the Director of Stanford Deep Data Research Computing Center, the Director of Science and Technology at Stanford Healthcare Innovation Lab, and a lecturer at Stanford University. He has been working on distributed and parallel computing applications since 2008. Currently, Amir is an active researcher in the VA Million Veteran Program, Human Tumor Atlas Network, the Human Biomolecular Atlas Program, Stanford Metabolic Health Center, and Integrated Personal Omics Profiling. We will reserve the last 5 to 10 minutes of this session for questions and answers, so please feel free to place any questions that you might have during the presentation in the questions queue in the GoToWebinar toolbar, and we will be happy to read them out loud at the end of the session. At this time, I will now turn it over to Amir.
Thank you so much, Erica. Can you see my screen right now?
Yes.
Okay, perfect. First of all, thank you so much, Erica and Dr. Gautam Nistala, for organizing this event. It's an honor to be here. Just a bit of background about myself. My career in medical research started out of a tragedy in 2014 when my wife, Somera, she was diagnosed with stage 4 cancer, and in 6 months, actually, I'd lost her to cancer. So I remember, before she passed away, I dedicated my career to medical research. I went to Duke Cancer Institute, and I was talking to this biologist, and he started talking about microRNA, messenger RNA, mature RNA. It was so intimidating. That was the first time as a computer scientist, as someone coming from the engineering department, feeling that overwhelmed and saw the gap. And I'm going to talk a lot about the gap between engineering department and School of Medicine. So here's the outline of my presentation. First, I'm going to talk about precision medicine needs and challenges. Then I will talk about disruptive solutions that we created at Stanford, my PhD, personal health dashboard, real-time alert system for COVID-19. Then I'm going to talk about Hummingbird and Swarm for optimizing computational and storage. And finally, I will talk about Stanford Data Ocean. So this is actually a study published in 2015 in Nature, and it's still true. It says that the top 10 highest grossing drugs in the United States help only 1% out of 25 who are taking, or 1 in 4 of the people who are taking it. So what does this mean? Does it mean the medication didn't work? Actually, the medication worked. The problem was physicians did not have enough information to predict if a medication would respond positively for an individual or not. So lack of information was the major problem. So what's important here is that suppose that you want to go from point A to Z, right? You're in Belgium, you want to go to Germany. What would you do? You would, of course, going to multiple layers of information, right? Wildfires, if you're going from North Carolina to California, you got to consider that. COVID-19 restrictions are important. Traffic is important. Every layer of information would help you to better understand and to get there faster and, of course, more safe and sound, right? Similarly, when we talk about our health is a product of microbiome, mainly our gut bacteria, our genome, environment, our diet, what we're eating, that creates our metabolism. Metabolites are all the small molecules in our body. And every layer of information here would help physicians to better understand the health of their patients, right? And this is a quote from a Greek physician 2,500 years ago, saying it is more important to know what sort of person has a disease than to know what sort of disease a person has. So we have to collect all these layers of information. So what's the challenge? Well, of course, this is what's happening right now. A tsunami of data is approaching the healthcare industry. And on the graph, you can see that we are generating exponentially genomics data. And the Moore's law is saying that every 2 years, we're supposed to double the CPU performance, but we're not doing well on that end. I'm just giving you an example here at Stanford Center for Genomics and Personalized Medicine. We collected over 2 petabytes of data just around Dr. Michael Snyder, the chair of genetics. Now, if you want to store 1 petabyte of data naively on any major cloud provider, it will cost you monthly $20,000 per month, right? So clearly, the cost function is rapidly changing toward computation and storage. And we definitely need new computational and storage systems. So what are the deep data needs and challenges? There are 4 needs that we have to consider. Number 1 is data acquisition, data collection at a scale. Second one is data storage. Where do you want to store that data? Data distribution is the third one. Where is it located? In different continents, different cities. And then we get to data analysis, the AI ML side of it, right? And when we want to propose any solution, this solution has to consider these 3 major challenges at least. The number 1 is the scalability. If you want to do anything in precision medicine these days, if you want to publish in a high-profile journal, you have to show that your algorithm works for a large number of participants, right? Otherwise, it would be really hard. Like if you come to me and tell me that your algorithm works for 4 people, 10 people, it's going to be really hard, to convince me that this algorithm is actually working for a large number of people. So scalability is one of the major pieces. The second one is interoperability, which is intertwined with the scalability. Of course, your algorithm works for Apple Watch. It doesn't work for Fitbit, so you're going to lose a large number of participants. Your algorithm should work for different cloud providers. So definitely interoperability is important. The third piece is security and privacy, which is the foundation of any medical application. When we talk about scalability, I typically refer to that as a dragon with multiple heads, because it's just not about infrastructure scalability. We have organizational scalability, we have team scalability, and of course, UI UX is going to be a part of that. And privacy and security, of course, is like an angel of death. When it comes, it's over. But what is the biggest problem? The biggest problem is the gap between engineering departments and a school of medicine. And this is actually a quote from Jeff Bezos, the founder of Amazon. He's saying that communication is a sign of dysfunction. It means people are not working together in a close, organic way. We should be trying to figure out a way for teams to communicate less with each other, not more. And of course, the number 1 enemy of scalability, inefficient and unnecessary communication. I'm going to talk about it in a sec. So here's the deal. This is how we are forming teams in a school of medicine. Let's say assume a team in a school of medicine is like a soccer team. We have 4 positions: goalkeeper, defender, midfielder, and forward players. So if we assume that data scientists are forward players, this is how we are forming teams in a school of medicine. Everybody want to be Cristiano Ronaldo, right? Messi. We're all, we for the last decade, people actually learned a lot of algorithm, which is great, don't get me wrong. But what's important here is also scalability, right? Data acquisition, data storage and processing, data distribution, UI UX problems. Then we get to the patient privacy, system security, because we're collecting a lot of data, right? It's important to understand that the value is in data. The value is not in the algorithm. And in the universities, what's happening is typically, this is what the model that we have. Scalability and security is actually handled by university IT, and the researchers are the forefront. And then when we talk about the university IT, of course, it's like they have their own HPC cluster. And in the backend, we of course have either Amazon, Google Cloud, or Microsoft Azure, right? But what's important here is that these researchers are disruptors, right? Their job is to bring things that they have not been scaled or they haven't been, studied. So the idea that somehow university IT would be able to keep up with these researchers is not going to work, right? So we still have a lot of frictions here. And I'm going to talk about it, of course, from the perspective of university IT. My team was, involved in that side, and then also from the researcher perspective. So what we need, of course, is we need to facilitate this communication, right? Again, efficient communication is going to be the key, and I will talk about it more. This is actually another misconception that this is how we're teaching, students, this is the service models in cloud providers. Like we have on-premises HPC system, we have infrastructure as a service, platform as a service, and software as a service. And we have these two things. There's a concept to call it pizza as a service, saying that you're in charge of everything, right? You have the whole kitchen. Then we have a community kitchen. We bring our pizza, cook it. It's more like an infrastructure as a service. And then we have pizza delivery and going to the restaurant. This is in fact just saying that you manage, cloud provider will manage. This is wrong because we know that there are shared responsibilities. And this is where the university IT is concerned, right? And they want to make sure that the researchers who are going to put, for instance, data in the public cloud, they're well aware of that. So I want to also touch another concept, and then I will start talking about our tools. One of the things that I really believe is that if we want to do anything, we have to at least understand our solution. Understanding the problem itself is a whole different level. It could take a year or two, but at least we have to understand our own solution. Let me give you an example here. This is a sectional chart used by pilots. And in this sectional chart, we have 3 airports. You can see here San Jose Airport, and we have Moffett, and we have Palo Alto Airport. And we're trying to, the question is, we're trying to deliver documents. We're not trying to deliver cars. We have 2 options. We have Boeing 747 and Cessna 172. What I have seen, mainly a lot, is that I see a lot of researchers that they tend to with sophisticated tools, right? It's hot, everybody is using it, so I'm going to go with that one. So the first problem with that is that if you go with Boeing 747, every takeoff and landing for Boeing 747 costs you $25,000 roughly, versus if you go with Cessna 172, it costs you $250. So the first thing is excessive cost, of course, right? When you scale this to thousands of participants or flights, then you're gonna, of course, see the impact. Here's the second important piece. So if you go with Boeing 747, right? So you would be able to fly from San Jose to Moffett, right? Easy. But the problem is you would never be able to land on Palo Alto Airport because it has a small runway. So basically, if you implement a solution using this, sophisticated, your solution would be restricted by the computational and storage needs, right? For example, you would not be able to run it on a cell phone, so you're going to lose a lot of participants, right? Developing countries are not going to be able to use that. So these are all important pieces that we have to consider during the research phase. And I'm going to talk about it, of course. And now I'm going to talk about a couple of some of our solutions. The first one is personal health dashboard. So wearable can track, of course, many things. They're very useful these days. They help you with monitoring heart rate variability, blood oxygen, and so many metrics. In 2017, our team was the first team to show that using heart rate, we can detect infectious disease, like Lyme disease in this case particularly, because when you get infected, your resting heart rate, we have an elevation in resting heart rate. And in this case, we have a resting heart rate elevated, and I'm going to talk about it more, of course, in the next slides. So Mike Snyder, the chair of genetics, I met him in 2017, and he told me, Amir, we want to collect a lot of data, a lot of participants' data, but we don't have such system right now. And so I started working on that application, but I got a lot of pushback from the university IT because they were concerned that we are going to put this data in the public cloud. What's going to happen? And totally legit, because we have PHI information, protected health information, that there was a lot of concern around that. University privacy and university security office wants to make sure that the privacy is, we protect the privacy of our patient. Then I came with this idea in my colleague and Xiao Li, that what if we store all the sensitive data, PHI information, on a secure environment. Let's say all the secure PHI information like first name, last name, email, zip code will go directly to a red cap that is actually running by the university IT. It's super secure. And then the data set coming from the watches the smartwatches, we collect it on the phone, de-identify it, encrypt it, and send it to the public cloud. And when I'm talking about de-identification, it's really important to code it, is that my resting heart rate, right? Let's say Erica's heart rate is 70 and mine is like 65. We are different, right? My data has to compare against my own data because I have a different baseline, right? 70 for me is totally not normal, right? Or 65 for Erica would not be normal. So what's important because of this uniqueness, right? We're talking about personalized medicine. This actually gives us an opportunity to transform our data to something unique. Let's say my data will be shifted 8,000 days to the future. Erica's data will be shifted 5,400 days to the future. So we can actually do that and transform it and reduce the risk significantly. So using this system, we were able to convince Stanford Security and Privacy Office, and they consider my PhD system as a low-risk system. Now, I'm not going to go and talk about the details of scalability here, but we created Kubernetes and tested multiple different weak scaling, strongest scaling, 95th percentile. If you're interested, please refer to our paper published in Nature Communication. We have done a lot of security analysis tests here. In terms of mobile phone, we have done a lot of penetration testing. If it's not the most secure in Stanford, it's definitely among the top most secure systems in Stanford. And we have 2 videos actually in YouTube if you're interested about how we designed this system, and we presented in the security festival at Stanford. At the beginning of the pandemic, we were actually looking for an application that we can show that this system works. Once the pandemic started, we formed a team of biologists and computer scientists, engineers. We had like 60 people. My team was like 30 people that they were dealing with the scalability, mobile app, of course, and security of the system. And there was another team that they were a team of biologists, bioinformaticians, data scientists, and coordinators that they were helping us. In 5 months, actually 3 months, because two months the paper was under review, we were able to pull 5,300 users' data, right, at scale. So it's real time. We would collect this data, and they were donating their data, and we would give it to the data scientists. And they were retrospectively creating and testing their algorithms to see, to create an algorithm to detect COVID-19. So this is, we created 2 algorithms, and this one is showing, as you can see here, elevated resting heart rate, and there's a big bump. And this is a day that there is a symptom onset, that you notice the symptom, and then this was the test date that they got tested positive. But you can actually predict this using the resting heart rate we were showing. So in up to 10 days and medium of 4 days before first reported symptom. This was the first time again that our team was in charge of the scalability and security, and the other team was developing the algorithms. Once we finished this paper got published in Nature Biomedical Engineering, we decided to go and create a real-time alert system. Can we alert people in real time? That was the question. And my team at this point was under a lot of pressure by the data scientists because they were asking us to give them more data. One question was, give us like 2 years of data. The other one was like another request was like, give us millisecond data. Those of you who are familiar with APIs for this wearable data, when you pull, for example, Fitbit data, it has a 150 calls per hour limit, and you're collecting heart rate, steps, and sleep. And if you want to go like for 2 years of data, collecting that, de-identifying, encrypting that data, it would take 8 hours. You have to run the app 8 hours. So we were under a lot of pressure by our customers also. And then at the same time, data scientists were asking us that our algorithm is not working. You got to give us more data. So this was actually a day that I remember as one of his Fridays in November. It's like 5:30 p.m. I was sitting with my colleague Arash, and started and thinking that maybe we can create a new algorithm. And so we started working on that, and on the Monday we deliver a new algorithm. And the idea behind this is this one coming. So again, our health is a product of microbiome, and genome, and environment, and the metabolism is the conversion of food, fuel to energy to run cellular process. And we have this process called homeostasis, of course, it balances our body. But when we look at this one, you see that when you start eating something, your genome would not change. Of course, your germ lines or what you got from your parents is not going to change over your life. You have somatic separate thing, but it's constant pretty much. And then after a while, for example, if you drink milk, after a while, like say in 2-3 hours, we have this if you are lactose persistent, right? Your body will populate a protein enzyme called lactase that would help you to digest lactose, break it down into sugar, into glucose and galactose, right? And after a while, in 3 hours, we see that the glucose level would go up in your bloodstream. This is why these clinical tests, majority of them, when you go want to take a test, they will tell you before taking the test, like 8 hours before that, make sure to not eat, fast, right, for 8 hours. The reason is that if you eat something, then there will be a lot of noise here, okay? Now, I'm here giving you a talk, and this is my watch is actually here. Let me see, what is my heart rate? Right, 87. And if I give you my heart rate, right, and I'm not walking much, so without giving you the context, I'm giving a presentation, but if I give you this data without telling you what am I doing right now, it would be really hard for you to, you potentially may say that, oh, there's something wrong with this person because it's not moving, their heart rate is really high. So the point that 2 years of data without the proper context would help you to infer anything is totally wrong, right? We're adding junk data, right? And it could actually bring some noises. I was traveling 2 years ago. I was, going through a lot of emotion during the day. So it's just really difficult. It would not help us to infer much. The idea of going with the millisecond, of course, is it possible that I get infected in millisecond and then the other millisecond I would not be? Yes, it is. In theory, of course, it's happening. But what's we observe in the first phase of our study was when you get infected, right? We see a resting heart rate elevated for like 2-3 days up to 2 weeks, and it goes even for long haulers. It's like multiple months. So going that deep would not really help. So what we did here was like, what if we focus this window, set it for midnight till 6 a.m. Why? Because that's the time that people are resting, right? They're not going through, much emotions compared to during the day, of course, again. And based on that, we created an algorithm called night signal. So we would calculate average resting heart rate overnight, and we pull 2 weeks of data. For every night, we calculate average resting heart rate. Then we calculate the median average resting heart rate over 2 weeks. And that, in our algorithm, considered to be the baseline. All right. Using that baseline, we propose an algorithm, a state machine that I will talk about it. That we see that if for 2 consecutive nights, your heart rate, your resting heart rate, or average resting heart rate, over 4 heartbeats over the median resting heart rate. This is so we will collect data, send it, de-identify, as you can see, it's at 2027. And then this is the baseline. And this is for 2 nights. You can see here, the resting heart rate is actually, the average resting heart rate is over 4 heartbeats over the baseline. Then we will give an alert to our participants. And it was sent it, of course, to the phone, and on the phone we re-identified, decrypted, re-identified, and you can see this was February 2021. So again, the whole thing worked really well, and we were able to predict this, and the sensitivity of algorithm was 80%, and it works for Apple Watch, it works for Fitbit, and again, in terms of sensitivity, specificity, we're much higher. It's a very lightweight algorithm. It's just average. It is median. He didn't use any sophisticated library or API. And the beauty of this system is this state machine. I feel like this is a concept that we have, like deterministic finite automata from in computer science. We were for the first time that we brought the concept from computer science and published it in Nature Medicine. And the algorithm is really lightweight. Right now, it's running on the phone. If you're interested, you're welcome to join our study. Yeah, this is basically with a Cessna 172, we were able to get into Nature Medicine. It's just simple things, but understanding the problem, and of course, understanding the solution itself, it helped us a lot to scale this algorithm. The MyPhD system right now is available at myphd.stanford.edu. We're offering this to different universities and folks who wants to launch their study, helping them to collect their data. So if you're interested, again, myphd.stanford.edu, please let us know. The second part of my talk is going to be around optimizing computation and storage. And I started working with VA MVP, Million Veteran Program, since 2016, and their goal is to sequence 1 million veterans. And when you get to 1 million genomes, right, when you're doing pre-processing, if you can save $1, it costs you $1 million, right? You can save $1 million. So the question that we see a lot here is that there's so many different virtual machines in different cloud providers. Which virtual machine instance is the cheapest one for every stage of the pipeline? Because we know bioinformatics pipeline is like a set of stages, right? You start, for instance, for haplotype color, start with the PWA, sequence alignment, and there are a lot of stages. Every stage is like a human, a different behavior. So which machine is the cheapest one? Which one is the fastest one? Or which one is going to give you the most cost efficient result? So that was the question. We created an algorithm, and this is actually what you see when you go with AWS, of course, which instance is going to be the cheapest, fastest, or most cost efficient, because some of these applications are CPU intensive, some of them are memory intensive, IO bound. So we created this algorithm that's actually using profiling. It profiles these tools, and it helped us to find out these cheapest, fastest, and the most cost efficient instances. And this was actually recently published, a blog post that I had an honor to work with three wonderful collaborators, Gautam, Paul Saxman, and Sojaya Srinivasan. You can see here, it's execution time in minutes. It's for BWA, for alignment, and this is cost in dollar. These are the instance families, different colors, and this is the number of virtual CPUs, because BWA support multi-threading. So when you run this, if somebody naively like go with the i3 instance versus something like C5A, it's almost $6 different. Go with 1 million, $6 million. So at larger scale, when you're running something a lot, definitely such solutions are important. It would help to deliver affordable precision medicine. The other work that it was another collaboration with VA MVP, is around called Swarm, a federated cloud framework. And the idea here is that at the end of the day, there would be data sets all over different cloud providers, right? Data centers. And let's assume that Stanford has everything on AWS, UCSF put all of their data on Google Cloud, and providers, Google Cloud providers right now, they're providing, public data. They can make it publicly available and for free. But the problem is that there are so many private data sets, of course. So if you want to move these data sets from one cloud provider to another one, you have to pay egress fee, right? That's one. The other thing is that once you make a copy going with a centralized solution, then you have to pay for the storage. So in this case, like we have four different, so the storage cost would be 4 times, right? The other thing that is important is that every time you are making a copy, you're increasing the risk, right? In terms of security and privacy. So, but the question is, do we really need to move these data sets? Let's say I'm working on diabetes, and there's a data set on Google Cloud and one data set on AWS. What if we first focus on the region of interest and see if there is any patient, right, that this patient actually has that mutation? Let's say a cardiac disease, I'm interested in RBM20. We first go and focus on the region of interest and see if there is a deleterious, damaging variant inside that region. If so, then we only collect that patient's data or those variants, compress that and see which one is actually smaller, move it, encrypt it to the other side, and then do the computation. That was the idea behind SUAR. It's actually helping us to reduce data motion significantly. And we did two applications here, annotation and allele frequency. And for one of these experiments, we showed that it's like moving 500 gigabytes versus just 4 kilobytes for allele frequency. And we compare Google BigQuery versus Amazon Athena. You can see that this one is actually runtime, but they're charging based on the amount of data being processed, and Athena is actually doing really well here. And it's a great tool for such analysis. But this was another application that we published in Bioinformatics Journal. Now I want to talk about unlocking deep data for precision medicine. So it's a serverless system. So I personally believe that in order to get to precision medicine, right, we definitely need we need a new generation of bioinformaticians. We need to also tap into the precision learning, personalized learning. This is our paper published in Nature Biomedical Engineering. It's been accessed 100,000 times. Let's divide this by 5, get to 20,000 unique users. Let's say assume we have 20,000 readers. Divide that by 2, and it's like 10,000 people actually went through this whole paper. And there are two sections in Nature papers, right? There's one is a data availability, and the other one is code availability. And so the next step for a researcher is to download this data set, of course, right? You may not even have that much space. The other thing is that to configure that. So it's going to be hours of your time to just configure it, download it. It's a lot of work. What if we have a system that with one click provides the data and it would give you access to the code at the same time? So that's what we created called Stanford Data Ocean in collaboration with Amazon Web Services. We developed this on a service workbench, and we have a set of modules and all of these data sets that we collected, for example, for COVID-19. We published that in Stanford Data Ocean, and right now we're looking for users, if beta users. If you're interested, please scan that QR code and contact us. And it's actually helping us a lot in terms of it's a fully managed system, of course, would help us to increase the productivity, and the users can focus on the business logic. Equity is important for us. We are trying to help with the middle class, and that next generation of bioinformaticians. And in terms of standardization, again, that's really helping us to create AI/ML friendly data sets. In terms of ethical AI/ML, we work on de-identifying synthetic data sets and going with the explainable AI. And we provide unique data set. As I said, there is no research lab releasing wearable data these days. We're the only one that's publicly available, our data set. And if you would like to play with wearable data, definitely play with this. Join us in Stanford Data Ocean. There's some of the things that I have done, since 2017. I created a program called in genetics department for computer scientists, that we recruit graduate students coming from computer scientists, engineers to come to the School of Medicine. And also I created a course called Cloud Computing for Biology and Healthcare, and offered for the second time this year. Last year it was we had Eric Schmidt, Eric Topol, Mark Rosinovich, and Mike Snyder. This year actually we had Paul Saxman, who is the head of the Academic Medicine Solutions Architecture at AWS. And what's important here is that we need people actually from other departments to come and join us and help us to solve these problems. And we'll talk about it more, but this is actually one of our interns.
I'm Thomas Beck. I'm a third-year medical.
Let's get this one. So Arash was actually, he joined us in summer 2018 as an intern with background in security and privacy. He didn't have any background in biology, and in 2019 he joined us full time. And as you can see, that 2021 we published his papers, and he's the first author of this real-time alert system in Nature Medicine. I'm so proud of him. He has done a lot of great things. And this is Thomas. He's a medical student, physician, and he's talking about the course. I just want to share this with you.
I'm Thomas Beck. I'm a third-year medical student at Stanford. And ever since I've been at Stanford, I've gotten really interested on how we could leverage all of the advancements that has been made in computer sciences to improve healthcare. Scalability is definitely an important thing to learn about, because before you set out to build an infrastructure to process your data, you want to know that it's going to be able to help more than just a handful of patients in a feasible manner. And of course, HIPAA compliance and security is important in developing any sort of cloud computing infrastructure, because I think the average person is already a bit hesitant in using this technology because of security concerns. But what I took away from this course is that these infrastructures are actually much more secure than what we have already in the hospitals if properly implemented.
So we need more physicians like Thomas, and we need more computer scientists like Arash to come to School of Medicine, people from different background, and they should come. And this is actually what we have done. We created a center called Stanford Deep Data Research Computing Center, that we are bringing people from other disciplines, like a pilots, right, artists, to come here and tell us how to solve these problems, because they can totally, give us a solution that is way more efficient than what we're doing here. So again, healthcare is universal, and everybody should contribute. So if you're interested, please contact us. We'd love to collaborate with you. And at the end, I would like to thank my colleagues, because without their help, of course, we would not be able to accomplish this. Of course, I just want to also make sure that especially these 4 people at the top: Dr. Somali Dada, Director of Research IT at Stanford; Michael Snyder, Chair and Professor of Genetics; Dr. Frank Mueller, Professor of Computer Science; and late James Morrison, who was my non-academic advisor. He was always, supporting me and asking me to work on medical research. And definitely Amazon Web Services collaborators, especially Paul Saxman, Gautam Nestella, Dominic Young, and Ken Harris. So with that being said, I'd be happy to take your questions.
Thank you, Amir, for sharing your experience. As he said, we're going to go ahead and move to the question and answer portion of the session. The first question is, for those that would like to contribute to the field of precision medicine, what do you think is one thing that would be a good first step?
Yeah, I think the first thing, if you're an engineer or you're coming from other departments, is the gap, right? It's intimidating. What I would suggest is that you contact a physician or a biologist first, and see what they're doing, what are the applications, and instead of learning, because typically we tend to think that, oh, I don't understand biology, it's really hard, I have to take some biology courses. That's good, but don't worry about it. Just focus on one application, one project. That's how we learn the most. And let's say, for instance, genomics, you go and work on the field of genomics, specifically on variant calling. Focus on that, get it done. You will learn a lot, and then go to the next one. Don't worry about proteomics, transcriptomics. No worries. That's the biologist's job. So just help them, with the one project, and then you will learn a lot. So that's my recommendation.
Thank you for that. Another question is, what are some challenges that you see in bringing such cutting-edge research approaches in precision medicine as presented by you to mainstream healthcare?
Yeah, I think moving from the research to clinical settings, of course, is a whole different level, and we need explainable AI, right? We have to be able to explain why our algorithm is working and why is it not working. So that's why, an algorithm like Night Signal, it would be much simpler for you to explain that. I think that's the key. You know, we need to make sure that people will trust our algorithms, right? And the other thing is focus on data as much as you can. Data collection, security, and privacy. I would say those are the major challenges from my perspective. And of course, teamwork. It's a lot. Efficient communication. That's going to be the you know, the main challenge, the gap.
Okay, thank you. And I do believe, talking about some of the collaboration that you had with Dr. Gautam Mistilla, who I believe is on the call, that might have been some of the challenges in perhaps bringing some of this research to bear, and making sure that you're able to get all your data processed. And
Absolutely, yeah, definitely. And again, you know, this, I feel like the Data Ocean would help us a lot. Stanford Data Ocean, this collaboration with the Stanford Amazon Web Services would help us a lot to help people to learn about these, you know, without being concerned about bringing data sets and, you know, installing and configuring algorithms, and just learn about it. You know, that's what we're trying to do. We help you to quickly, you know, learn about these data sets and the code, and help you to facilitate, you know, create a common language between engineers and biologists. So I think that's where we are going with Stanford Data Ocean, and with Amazon has been super supportive, and we're very thankful for that.
great. I'm just going to check really quickly to see if there are any other questions that are coming in. Let's see. There is one other that has come in. How hard might it have been to sync up with perhaps IT on your campus with setting all of this up?
Very hard. That's definitely super hard, you know, at the beginning, as I mentioned. But then we were able to convince them, right? Like this is a low risk system, and again, as I said, they are coming from the fact that, and I totally understand that, because there are several layers that they are shared responsibility. Who is going to be in charge of that, right? Their concern is coming from that end. And if you can show that, again, one of the tricks that we used was like, okay, you know what, all the sensitive data will be handled by the university IT, and then we focus on less sensitive data and create an API so that this system can talk to each other. I think that would be a great start. But as I said, you know, recruiting computer scientists would be really helpful. Someone who would be able to easily communicate with them and explain why such systems are really necessary, because there are many labs, and of course, from the university perspective, they would go with the you know, the demands, right? To say, okay, out of this 100, 80 of them are saying they want to work on genomics, so we provide these APIs. But in reality, those researchers are disruptors. They want to go with different solutions, again, those that they haven't been scaled. So I think we need to equip our bioinformaticians and biologists. Again, you know, try to bring computer scientists, engineers to their team as a collaborator, and learn quickly about these systems, about scalability and privacy. That would help a lot.
Thank you. Another question. In your night signal, does the heart rate depend on the stage of sleep and level of unconscious activity? Example, scary dream versus pleasant dream during REM sleep.
That's an excellent question. And actually, we didn't, you know, use the sleep. We focus on step. We collected heart rate and steps, and we consider when you're not moving, right? The step count is 0. The corresponding heart rate is considered in our system as a resting heart rate. But totally, that would be a smart move, you know, to focus on the sleep time, and that you know, interval, that would help you a lot. But yeah, in our case, because for some watches they don't report sleep, we chose step and heart rate.
Great. Another question. Are you open to giving advice to startups who are developing explainable AI on the cloud for commercial usage? And if so, is there a best way to contact you?
Yeah, yeah, that's a tricky question, but happy to talk. Again, my email address, I can send it to you. You can search, Google my name, Amir Bamani, and there are some email addresses that you can communicate, and happy to help you in any, in a way I can.
Okay, and I think this might be our last question. Has HIPAA been a roadblock in being able to use real data? And if so, what are some specific examples and how did you work around that obstacle?
I think everything at the end of the day is about risk. Yeah, there is no 100% secure system. It's a lie, right? If somebody comes to you and said that I have a 100% secure system, they are selling snake oil. Don't believe that. So what's important here is to make sure to separate, right? That's what we did. Separate sensitive data from less sensitive data. That's what I would do, and try to, like in this case, we shift data like heart rate, right, to the future because of the timestamp. And that would make it really hard for an attacker to re-identify that person. Again, the attacker could have an auxiliary data set, right, to run this data set that you collected against that and re-identify that person. But shifting data would help a lot in this particular case to reduce the risk. So focus on the risk, separate data, and try to, transform it. Again, this is precision medicine. Use this as an opportunity to transform users' data to something unique. That would be really helpful to reduce the risk. And of course, cloud providers like Amazon, they have the best practices, HIPAA compliance best practices. So follow those. Logging, auditing, and all those things would be really important.
Definitely, and that is where our research team would love to help and partner with researchers just like you and those of you that are on this call. I want to thank you, Amir, for sharing your time and your expertise, and I'd also like to thank each of you that are on the webinar for participating today. If you have questions about upcoming sessions or wish to access recordings, you can follow the link that you see on the screen, which I am pulling up right now. I've also placed it in the chat, so you're welcome to access it that way to get other recordings that we might have. And that is also a way to reach out to our team as well. Before you leave, please take a minute to give us some feedback on today's session. A short survey will pop up on the screen as we close out. We host these webinars for the research community, so any feedback that you have is valuable and will help us to continue to deliver content that the research community cares about. Thank you so much for joining us today, and we look forward to seeing you again soon.
Thank you very much.